Hey everyone, and welcome. In today's explainer, we're diving into a really fundamental question for anyone who works with data. How do you go from just a sea of numbers to a conclusion you can actually trust? We're going to cover the statistical foundations that make all of that possible.
So, let's get real. You've got data, right? Maybe a whole mountain of it. Transaction logs, user metrics, you name it. But by itself, data is just stuff. The whole point, the real challenge, is to turn that raw material into knowledge you can rely on. So how do we make that leap from a pile of numbers to a genuine insight? That's exactly the journey we're on today.
To even start that journey, we need a common language. A way to talk about uncertainty, chance, and all the randomness in the world. And that language, my friends, is probability. It's the absolute bedrock of statistics, giving us a formal way to reason about things we don't know for sure.
At its heart, the classic idea of probability is just a simple fraction. Let's take a coin flip, the perfect example. You've got two outcomes that are equally likely, right? Heads or tails. The number of outcomes you're interested in, let's say heads, is just 1. So the probability is simply 1/2. This super simple idea is the launchpad for everything that follows. Okay, let's build on that with a couple of key concepts. First up, a random variable. Sounds kind of fancy, but all it is a way to pin a number on a random event. So, if we toss a coin twice, our random variable could be the number of heads we get. It could be 0, 1, or 2. Simple. Then, we have the probability distribution. You could think of this as the complete roadmap for our random event. It's the rule that tells us the exact probability for each of those possible outcomes.
So probability gives us this really powerful theoretical way to think about randomness. But how do we connect those clean theoretical ideas to the messy real-world data we're actually working with? Well, the bridge that connects theory and reality is sampling.
And here's where we get to one of the most powerful and honestly kind of mind-blowing ideas in all of statistics. The accuracy of your sample depends almost entirely on its own size, not on the size of the whole population it came from. A well-chosen random sample of 1,000 people can paint just as clear a picture of a massive country as it can of a tiny town. It's all about the quality of the sample, not the size of the ocean it came from.
But, and this is a huge but, not all samples are created equal. This quote really gets to the heart of it. It's only when every single item in your population has a known real chance of being picked, that's a probability sample, that you can objectively measure your potential for error. Without that, you're really just guessing. Randomness is our guarantee of being objective.
All right, so we've got our language, probability. We've got our bridge connecting it to the real world, random sampling. Now let's get into the good stuff, the actual tools of statistical inference that let us use that small sample to draw some really powerful conclusions about the entire population.
The simplest tool in the toolbox is called point estimation. It's pretty much what it sounds like. You take your sample data, you calculate a number like the average, and you say, this is my single best guess for the true average of the whole population. It's direct, it's useful, but it doesn't give us any clue about how certain we should be.
And that's exactly where interval estimation comes in, to give us a better picture. Instead of just one number, we calculate a range of plausible values, what we call a confidence interval. Now we can say something way more powerful, like we're 95% confident the true value is somewhere between x and y. It doesn't just give us an estimate, it tells us how much uncertainty we're dealing with, which is a much more honest way to look at it. And finally, we have hypothesis testing. This is the tool you pull out when you want to answer a very specific yes or no question. Like, did the change we made to our website actually increase sales? Or is this new manufacturing process better than the old one? Hypothesis testing gives us a formal, structured way to weigh the evidence and make a decision.
Let's do a quick walkthrough of how this works. You always start with a null hypothesis. Think of this as the skeptical position, the status quo, the nothing interesting is happening here idea. The alternative is the new claim, the thing you're actually hoping to prove. Now, of course, you can make mistakes. A type I error is a false positive. You think you found something, but you didn't. A type 2 error is a misdiscovery. You missed something that was actually there. And the final verdict often comes down to the p-value. If that p-value is really, really small, it means your data looks very strange under the null hypothesis, which gives you a good reason to reject it and go with your alternative idea.
Okay, so once we have all these powerful tools, a really fascinating question pops up. What exactly is the probability we've been talking about this whole time? As it turns out, not everyone agrees. And this disagreement leads to two major schools of thought in statistics, two totally different philosophies for how to interpret our results.
So here's the core of that divide. The frequentist approach, which is probably what you learned first in school, says that probability is a long-run frequency. For them, a parameter like the true average for a whole population is a single, fixed, unknown number we're trying to figure out. The Bayesian approach, though, is different. It sees probability as a subjective degree of belief. For a Bayesian, that same parameter isn't some fixed point, but a whole range of possibilities that we can formally update as we get more and more data.
So how does that Bayesian thing actually work? Well, the workflow is this really elegant three-step process. First, you define your prior distribution. That's what you believe about something before you see any data. Then you go out and collect your sample data. That's your evidence, or what's called the likelihood. Finally, you use something called Bayes' rule to combine your prior belief with your new evidence. The result is an updated belief, the posterior distribution. It's a formal system for learning from experience. It's pretty cool. And this brings us right to our final question for you. We've gone all the way from raw data to the language of probability, we've crossed the bridge of sampling, and we've explored the tools and even the philosophies that guide them. So, as you face your own mountains of data, which path are you going to take? The objective long-run frequency of the frequentist or the belief-updating journey of the Bayesian?
If you found this explainer helpful, we'd really appreciate it if you could take a moment to like it, share it with a colleague, and subscribe for more deep dives into complex topics. Thanks so much for joining us, and we'll see you in the next one.